Hi friends, we are back with the fifth video in our Robotics Software Pico degree. In this video, we will learn about navigation. So if you are following this series, we learned about how to set up our environment. So how to set up Webots with ROS. We also learned about how the robot navigates with teleop. We learned how to make URDF of any particular robot. Also, in last video, we learned about mapping. So if you have not checked the videos, do check. The link of playlist is in the description. So this is one of the most important videos in this series. So we will be making a concept video for navigation. So once that video is released, the link of that video will be in the description. When we commonly imagine a robot which comes to our mind are the robots which can move from A to B. For any robotic system, navigation is one of the crucial parts of its software. To categorize navigation into some parts, robot can be broadly classified into two parts. One being the robots which have predefined path, so they are known as AGVs, automatic guided vehicles, and one which makes path and does obstacle avoidance, which are AMR, autonomous mobile robot. Also, under the hood, robots may have different types of planning algorithms, like it may be using deterministic algorithms like A star, Dijkstra, etc. Maybe they are using probabilistic algorithms like RRT, RRT star, PRM, etc. And also mechanically, robots may be different, like robot may have 3 wheels, robot may have mecanum or caster wheels. Also, robot may be bipedal robots, like we see those cool Boston Dynamic robots. So navigation is different for these different robots. So today we are going to learn about Movebase, which is a very good versatile infrastructure which will consider all these different kinds of robot and give us a framework to suit our own robot. So in today's video, first we will understand how the Movebase works, what are the different moving parts of the Movebase, and finally we will configure Movebase for our particular robot. And at the end of this video, you will be able to move your robot from A to B location just by merely clicking on the point. So let's first look at the glimpse and then we will go into details of Movebase. So after having glimpse of how the robot navigates, now let's take a step back and understand how humans navigate. For us to navigate, we need some trigger. So for example, let's say you want a coffee. In order to get a coffee, first of all, you need a map. You need to know where the coffee place is with respect to your house and which all roads are accessible, after which you will have the knowledge of which roads are faster and which roads have less traffic. So for robot, that is like a global Costmap where it knows where the static obstacles are and which place has a lower cost. After that, you will plan a path and you will know which main roads and highways to take in order to reach the place. That is nothing but a global planner for a robot. Once you have a global plan, you start following it. For you to reach the place, you need to know where other cars and humans are around you. So that is nothing but a local cost map for the robot. Once you have the proximity of people, you will plan a path around them without hurting them. That is nothing but a local planner for robot. So you see here different level of decisions were taken by different things, because your global planner, that is when you decided that which roads will you take, you did not know where the people and cars were. So both the planners have their own responsibility. Also, some other things you will need are where your body parts are. So that is nothing but TF of robot. TF is where the wheels and sensors of the robot are with respect to some stationary point. And after doing all this planning, you will steer, you will walk, or you may brake. This is how human navigates. So now when we look at the navigation of Movebase, all this will make much more sense. So now let's discuss what is Movebase package. So Movebase package is like a framework where you can plug in different global and local planner and different paradigms of your cost maps for it to work which suits your robot. So now on the right we have our image which we discussed, and here let's see the analogy of how Movebase works and how human does navigation, where even Movebase takes in map from a map server, then it updates the global cost map, which is gone to the global planner, and global planner computes a big path of how to reach the goal. Then it goes to local planner in order for taking smaller decisions of how to avoid obstacles. For local planner, we have local cost map for its assistance, and we have sensor data to know where the cars and humans are. Once we have a local plan, we get a command velocity from Movebase, which is the output, and our trigger is the Movebase. Also, we had TF in our case. So here we have AMCL and different sensor transforms. So Movebase takes in this TF, and this is how Movebase is configured. Wasn't that easy? It was exactly how we discussed human does. I will share this page with you in the description, and you can go through the basics of Movebase, and here there are APIs where how to talk to Movebase. There are different publishing topics. As you see here, command well is what Movebase publishes. You have different services to clear the cost map, and you will have different parameters like base global planner. These are interchangeable. So Movebase has done a great job in giving us many different global planners. We will look into detail when we see how we have configured the Movebase. So you can have a look at this page and understand it thoroughly. So after learning about how Movebase works, let's get our hands dirty and let's implement Movebase in our project. If you guys are following this tutorial series, you must be knowing that we are using this repository named Robotics Degree. If you do not have this repo, watch the first video, or you can git clone the repo. We have a source folder, and inside this we have git cloned this repo. So for today's video, we are going to use Movebase branch. So I will git check out Movebase branch. And once you check out to this branch, you should come 2 folders back. And now we will first of all do ROS dep. So this will install all the dependencies for our navigation project. So it will install Movebase, it will install different planners, cost map, etc. for you. Hit enter. So it's installing AMCL for me. You see here it also installs different planners like Carrot Planner, DWA Local Planner. Once everything is installed, you will see all required ROS dep installed successfully. So now you are ready to catkin make. When you do catkin make, it will build your project. And if you guys are following this, you must be knowing that we have a bring up package inside our repository. Today, we will learn the navigation package. So in this package, pretty much we have 3 folders. And in our master.launch, we are just calling the movebase.launch. That's it. So now let's look at the Movebase launch file. So if you are following the video correctly, this will exactly go with what we learned, where we will initialize a Movebase node. It will take in bunch of parameters. In a moment, we'll look at all these parameters. So these are the Costmap common parameters, which are common for local and global Costmap. So we namespace it with global Costmap. Same thing with local Costmap. Then we load some special parameters for local cost map, some for global cost map, and finally we load parameters for our local planner and our global planner. So now let's go in configurations. So first of all, we will look at base local planner. So in our case, we are implementing the default base local planner, which is trajectory planner. If you want to get fancy, you can try other local planners like base local planner, DWA local plan, tab, or model predictive control local plan. So it depends on different applications. I would recommend you try different planners and see the effect. So for today's video, we will configure the trajectory planner. So we have some configuration, which is minimum velocity, maximum theta, and acceleration. And we are having holonomic robot, that is, it can turn in place. So these are the basic configuration. If you change this configuration, you will see its effect in your output, which is command velocity. Now we will see the configuration of global planner. In our case, we are using nav fn ROS. This is a default global planner. If you don't define this parameter, still your global planner will be defaulted to this nav fn one. Here also you have a couple of options. You can put global planner. You can also use caret planner. Will make you reach near the goal even if your goal is an obstacle. So you can try these different planners. After this, let's configure our cost map. So first we will look at common parameters for local and global cost map. So here we have two parameters, obstacle range and ray tracing range. These parameters are crucial because if you have a sensor with a noisy reading, it will give you bunch of obstacles around. But if you say that if there is an obstacle within 2.5 meters of my sensor, that is only when you put that obstacle in your cost map. And also this ray tracing range is the value where above this value you will clear your local cost map. To go into much more details, you can go to ROS wiki and you will see all the detailed parameters. Also, in the implementation, you will see that there is a green box which is 0.2 by 0.2 meter. So here we are defining a footprint of our robot. This is nothing but the size of robot. So while navigating, our planner considers that robot is not just a point, but it has some width and some height. Also, we have inflation radius. This is the parameter which bulkens our obstacle by 0.1 meter so that we don't go really close to obstacle or end up hitting an obstacle. After this common parameters, now let's see global cost map parameters. So in global cost map, we just define what is our global frame and what is the robot frame. There are many other parameters for global cost map as well. We will put the link of all these parameters in the description. Also, similarly, we have a local cost map parameter. I have tweaked many move bases for different robots. I feel this is the most important file. Here you define all your sensors. So if you have a laser sensor and if you want to put that laser data in the cost map, so you define your obstacle layer here and you define the parameters of your laser, like your laser name. You can define the message type of your laser, on which link your laser is publishing, and do you want your laser data to clear the cost map if the obstacle is gone, to mark the cost map, and finally the laser topic. We will see in the next video when we will be doing obstacle avoidance in detail. But this is a crucial point in Movebase configuration. So this was all about configuring our Movebase, and also we need to have a look at how we convert our command well, which is with respect to robot, to individual wheel velocity. So the following diagram says that in command velocity, we have two components, which is linear x and angular z. So if we have a linear x, that will be the same value for both the wheels, and for angular z, which will be an angular velocity, so we will have to multiply it with the radius, which is the wheelbase, and one of the wheel will get a positive velocity and one wheel will get the negative velocity. So if you see in the formula, where your left wheel will be linear x plus wheelbase into angular z, and your right wheel will be linear x minus wheelbase into angular z. And finally, when we have individual velocities of wheel, we divide them by radius of wheel, because at the end of the day we need angular velocity of individual wheels. So this is exactly written in our code, where we have a callback of our command well. So we take in the linear velocity and angular velocity, we compute by the formula which we just discussed, and we give our right wheel the resultant output, and that is how we are converting our command well into individual wheel velocity. Let's go see the output of our project. Let's do source first. Setup.bash, ROS launch, bring up master.launch. So you see here we have our world. Now pretty much you will be feeling this world as your own home, because we have used this world a lot. And now if I use 2D nav goal and publish a goal in any orientation, our robot turns and goes towards the goal. You should notice here that our red line is our global plan, which does not change very often, and our green one is a local plan. So if you see here, our green line changes continuously and it follows the global plan. This is exactly where you consider your robot's slippage, your sensor noise and stuff, in order for robot to reach the goal. Let's do it once more. And many of you must be questioning that, okay, I can make this work with Rviz. How do I programmatically give a goal to robot? So to answer that question, let's see ROS topic echo slash Movebase simple goal. When we echo this topic, you see here these coordinates are taken in the position. Our frame ID is map, which is our global frame ID, and this is the orientation. So now let's publish through terminal. So you must have understood that if we can do this with terminal, you can definitely write a C++ or Python node to publish this. And this is exactly what we are going to do in the application video. So ROS topic pub slash Movebase simple goal. When I double tap, it gives me the complete message type. So let me make this as map. And let's go to the bedroom. So I feel the coordinates are -6. Let's make y as 2. And let's keep orientation as 0 degrees. So if I publish this, You see here, robot started moving and this coordinate is the coordinate in bedroom. So you see here robot is also moving. In this implementation, we are assuming that there is no dynamic obstacle in the way. So that is exactly our second video where we will have dynamic obstacles and robot will go around it. So now let's see the configuration of our Rviz. So in our Rviz, pretty much you can add all these topics. For now, let me hide these topics. So you have a basic map. You can go to add, you can go to by topics, that is easier. And when you go near Movebase, you should be able to see all the topics where this is your plan. So if I do OK, it configured your plan. You can also configure other things like your cost maps, your footprint. So you see here, if I do footprint polygon, you see here we see the robot footprint. Similarly, you can also integrate cost map. So if I do local cost map, I should be able to see this. And also you can change the scheme of cost map. This looks cool to me. I'll be using this configuration. You can also rename this as local cost map. So you see here, this is your local cost map name. Similarly, you can configure all the planners, your footprint, and also robot scan. So this was all about today's video, where there is a lot of homework for you guys to check different parameters to see how your robot changes the behavior depending on different planners. If you have any doubts, you can definitely comment, and if you like the video, do share and implement the cool navigation. Thank you.